This afternoon session is called A Guide to High Performance Cold Form Steel Assemblies. This program, using building science principles, will illustrate how cold form steel framed assemblies can achieve project performance requirements. Specific emphasis will be made to fire resistance, acoustics, structure, and moisture resistance. There are 4 learning objectives within this course, and they are as follows. Participants will explore the inherent fire resistance of cold form steel frame assemblies using ASTM test standards. Second, participants will investigate how the principles of acoustical performance combine to provide high sound transmission classification, or STC, assemblies. Third, participants will learn the basic structural procedures to design and detail a simple, non-structural cold form steel assembly. And finally, participants will envision the required steps to control moisture migration in a cold form steel assembly. To that end, we have divided the program into 6 main topics. They are as follows. We'll give a quick overview on what exactly is cold form steel. We will explore the material itself, how cold form steel framing is manufactured, and finally, a quick look at the product line. Cold form steel framing is non-combustible and is the backbone for many fire-resistive assemblies. We will look at how a fire-resistive rating is obtained, what standards must be followed, and eventually the range of performance that can be obtained when using cold form steel framing assemblies. The science of sound, or acoustics, will be reviewed. Simple definitions of key terms will be discussed. High-performance acoustic walls will be illustrated, and some critical details discussed in how to maintain the required performance. In certain interior applications and in all exterior walls, moisture migration through the wall must be analyzed. This section will cover the physics of moisture migration and the critical application of these principles to control moisture migration. As in all components of a structure, proper detailing of cold form steel assemblies is essential. We will look at some recognized details. Finally, the last section of this course will involve a simple design problem and the ensuing solution. We will look at how we put all these pieces of building science together, fire, sound, structure, and come up with a good design solution. Cold form steel background. The primary elements of the materials that go into steel are iron ore, coking coal, and yesterday's Buick. I say that in jest, but in reality it's the truth. I've had the opportunity and pleasure to research the steel industry in the last couple of years, and it's gone through a tremendous transformation over the last 15, 20 years, from the way steel is manufactured, how it's produced, to its management style, to its global nature. Everything has changed about steel. And one of the things that got lost in all this is its sustainability. There has been tremendous changes in the way steel is produced in such a way that even though we claim that steel, 25% of the steel studs that we provide is recycled content, in fact 85% of the construction steel is totally recycled. One of the things I learned that was very striking to me, I had always assumed that aluminum was the most recycled building material, or most recycled material in general. It is not. If you take all those materials, aluminum, bronze, whatever, copper, you combine them all together, they still do not meet how much steel is recycled. And this is huge. The other side of the coin is energy consumption. And I want to take a moment and talk about sustainability because I think it is so critical in what we do in the construction industry. We're all concerned about global change, and so we watch things like carbon emissions and greenhouse gas emissions, and the EPA recently cited that the U.S. steel industry has reduced its greenhouse gas emissions by 47%. It has further reduced the energy consumption since like 1990 by 27%. So in reality, yesterday's Buick is today's steel stud. And what you're looking at in that top slide are coils of steel that are being shipped into a steel stud manufacturer. That's the way they arrive. They come from the mill. They're pre-coated with corrosion-resistant material. Typically, the benchmark of performance is galvanization, so it's coated in zinc and galvanized, and it's slit into the widths of sizes it's needed for the individual profiles. We call that the blank width, and then mounted on a machine or the cold form machine to process the eventual shapes that we need. The slide in the center is that cold forming process. As steel goes through the different dies and stages of the cold forming process, each time it does, each stage it goes through, it's bent a little bit more. And it's done to the final point of reaching the profiles that you see in that bottom slide. And those are the profiles that you will find in the building construction industry, starting with steel studs through here, runner track, drywall furring channels, Z-girts, furring channels, brackets, all coming from a cold form steel process. What we're going to focus on this afternoon is this guy right here, the C-stud or joist. It comes in thicknesses ranging from 25 gauge or 18 mil, 33 mil for 20 gauge, 54 mil for 16 gauge, up to 12 gauge or 97 mils. The shape that we see most common is this C profile, and the anatomy of a stud is as follows. This is the stiffening lip. It stiffens. This is what's called the flange. So the lip here's purpose is to stiffen this. The purpose of this flange is it carries the compressive and tensile forces when this steel profile is put in bending. The web is this member here, and it provides the depth, or basically separates the two flanges from each other, and the further apart the better it is from a deflection and stiffness standpoint. Getting over to the naming protocol for cold form steel framing, the first descriptor that you see is the depth of the web. It's 362 in this case, which stands for 3 5/8. The S descriptor is the style. This talks about the flange width, which is 250 in this case, which means it's 2.5 inches. And finally, the last descriptor is the material thickness itself, and that's measured in mils. I was very fortunate in my career, and I started out as a young man in the building construction industry. Furthermore, I started out in an R&D environment, and I really think the success that I've had over the years is based on the fact of those growing years in an R&D environment, or in what I would like to think of as an engineer's playground. What joy is it for a young man to build walls and then destroy them? How much fun is that? And that's exactly what we did every day. We were building profiles maybe similar to this wall that you see here, and I would put them in a vacuum chamber, which would evacuate all the air behind it, thus putting a uniform load on the face of that wall, deflecting that wall to a point of failure. And the purpose of that test was to determine the contribution to stiffness that the wallboard provided. And we would take those numbers and we'd plot it and get the Johnson's empirical elastic limit and all that kind of neat stuff and determine the contribution. Or we would put a ram on one side of that wall and rack it and determine the racking strength of that partition. But every day, even though I had that playpen to play with, the next lab over in our facility was the fire test lab. And every day I'd walk over there. I'd walk over there for morning coffee before I started. I'd walk over there for coffee break. I'd walk over there for lunch. I'd walk over there for an afternoon coffee break. I drank a lot of coffee in those days. Just to see what was going on in the fire test lab. And I just found it fascinating what was going on. And although the test itself weren't all that exciting, but the net result was cool to me. And maybe it's because I grew up in a Midwest environment. I grew up near Chicago, and I don't think anybody that grew up near Chicago does not have some sensibility to what happened in this area in 1871 when someone's cow kicked over a lantern and burned down all of the combustible buildings within the city proper of the city of Chicago. Or in the late 50s, there was a school in the city that burned and was the result, or resulted in the death of many, many children. Very sad event, and it all traced back to combustible building elements in a commercial application. So there's a huge sensitivity on my part to fire resistance. And there are 3 points I want to leave you with before I start talking about the fire test itself. And the first is that ASTM E119 is a fire resistance test. It's the standard that we test by, the industry tests by, and it is by design a comparative test. And I say that because it is not intended to predict the performance of a building element, and that element could be a floor ceiling assembly, it could be a wall, it could be a beam or a column. It's not to predict its performance in an actual fire event. Its design is to compare, let's say, different wall types and how they will perform in a test environment. So if I want to evaluate how a plaster assembly compares to a wallboard assembly, I run an E119. If I want to understand the difference between a metal stud or a wood stud, I run an E119. It is not designed to predict performance. Secondly, and that's tied to the third item that I want you to remember, when we run an E119, there are 2 components. We are solving a heat transfer problem. How much heat will transfer through, I've got the pointer on the wall right there, how much heat will go through that wall if there is a fire on one side of it. And the second part of the equation that we're trying to solve is at this picture down here. You see a hose stream, that's this guy coming in here. That is not designed to see what happens when a fireman's hose hit it, but in effect it's designed to show what happens if something structural, let's say I have a joist coming across the top of that wall, it fails and it falls into my wall. Will it fail my wall? Yes, it has something to do with the cooling and eroding effect of the water, but not the fireman's hose. In a post 9/11 environment, we were asked by developers to run fire tests to predict what would happen by a fireman's hose. And so we did a little analysis, and what pressures are we talking about? Well, you got so many variables. Is the fireman 100 feet away? Is he 10 feet away? Is he coming at it normal to the wall, or is he at an angle to the wall? More important, what are the pressures that's coming out of the pipe? He can vary that. He can change it to whatever he wants. He can have a water pressure coming out of that pipe that's called a water cannon, but that by design will blast all the walls out so he can find the fire without going through the building. Or he can fog the area to lower the temperature. So it has nothing to do fireman's hose. So let's get to the ASTM procedure at first. What you're looking at here is a concrete and steel yoke. We build a wall. That's what you're looking at here. The size of this yoke is 100 square feet as required by ASTM E119. Nominal 10 foot by 10 foot, and you can see this is the wall board underneath it because of the joints. You can pick out where the framing members are. So this wall is built exactly as you would want it to be, let's say, in a real life event. So behind it are metal studs at 16 or 24 inches on center. There's a track at the head, a track at the base, and wall board assumably on the other side. That concrete steel yoke is then clamped in front of the furnace, and a fire is started. This fire source was typically here in the United States natural gas. Almost all of it's natural gas here in the United States. I did have the opportunity in the mid-90s to go to mainland China, and we had to run fire tests to qualify for a project there. There we ran into an oil-fired furnace and huge learning curve on it. But anyway, getting back on topic, we build the wall within the yoke, we clamp the wall in front of the furnace, and up here, see this chart? This chart is the control of the furnace, the temperatures within the furnace that are being subjected to the other side of this wall must follow what's called this time temperature curve. And on the horizontal, you're looking at time in minutes. On the vertical, you're looking at degrees in Fahrenheit. The thing to remember here is it's a very radical rise in temperature. Within the first 5 minutes, the temperature exceeds 1,000 degrees within that furnace cavity. Anyway, 1,000 degrees, first 5 minutes. And this curve does actually simulate pretty accurately what happens in a natural fire event, except that in a natural fire event, at some point in time, all the combustibles will be consumed by fire and the fire load goes down. Therefore, the temperatures will start to drop on the unexposed side. Well, the heat transfer portion of it is straightforward. We install 9 thermocouples on the unexposed side. A thermocouple is like an electronic thermometer. It's measuring the temperature right at that location. And what we're trying to determine and control is of those 9 thermocouples, the average of those 9 thermocouples cannot exceed 250 degrees Fahrenheit plus ambient. Or you cannot have a single hot spot or one of those thermocouples exceed 325 degrees Fahrenheit plus ambient. That ambient being, let's say, it's 70 degrees in the fire lab when we start the test. That means you're looking at an endpoint of around 400 degrees. What's the significance of that 400 degrees? Well, it's critical. Years ago, there was a book written, a science fiction book, and it was about the culture that decided that reading books was bad for the mind. It corrupted the mind. So what they did is they burned all books. All books were banned. You had to give them up, and they would be publicly burned. And the temperature at which paper burns or starts to burn is 451, hence the name of the book, and then the movie was Fahrenheit 451. I say that is that's the point of pyrolysis for paper. So let's think a moment, if this is an office wall, and I have my desk right next to this office wall, and I have a garbage can full of my mistakes or paper that I've made mistakes on and thrown into the garbage can. I have a fire raging on the other side of that wall where the temperatures exceed 2,000 degrees. Is the temperature on my side of the wall at such a level that the waste paper in that garbage can will start on fire? If it does, you don't need the wall because you just breached it. And that will happen at 451. So the point of the test is to keep the temperature below that point of pyrolysis of combustible materials. The hose stream part. If we've gone for a 2-hour firewall, or not firewall, but a fire resistive rating, we rebuild the wall exactly as before and fire test it for half the time, or 1 hour. And immediately afterwards, we pull it away from the furnace and we hit it with, you can see it here, a hose stream. And that hose stream is at a specific distance and a specific pressure. And the technician will take that hose and just walk it back and forth, side to side, up and down that wall for a prescribed amount of time. And if water protrudes beyond the plane of the wall, that constitutes a failure. And those pressures are significant. I'm going to be walking through some partitions in the next few slides. But for example, at 1 hour, that technician is hitting the wall for 1 minute with the 25 psi wall water. At 4 hours, the pressure pumps up to 45 psi. The temperature goes to 5 minutes. So he's playing that water back and forth for 5 minutes. If you ever want to see a gypsum guy get sweaty palms, you have him stand and watch that test, because it is horrific. Okay, now we're going to start to build some assemblies. We're away from the building science side. We're doing assembly construction. And the thing I want you to remember from this standpoint, it's a question I've gotten many, many times over the years. What's the fire rating on my product? The fire rating on my product is 0, because it's not until I build an assembly like you see there with drywall and metal studs and I start to develop a system or an assembly do I start to get the fire rating. And that fire rating goes from that point all the way through to that point. That is where the fire resistance rating covers. We're going to start to build a wall. Metal stud construction, 18 mil, 24 inches on center. We've got a 3 5/8 drywall stud, a 125 flange, a layer of 5/8 Type X board on both sides. A little sidebar here when it comes to gypsum panels, and we're talking about fire ratings. There are 3 types of gypsum panels out there that come into play when we're talking about fire resistance. The first one is called regular core. You won't see any UL designs with a regular core panel. It has inherent fire resistance, but not enough where it can be used in fire resistive ratings. Type X board is the next type of board that's available, and that by definition it's a 1 hour board, which means, and I don't mean 1 hour by itself, when you take that 5/8 of an inch panel and you install it on both sides of a stud, it will give you 1 hour protection, or 1 hour fire separation, or a 1 hour fire resistance rating. So that is by definition a Type X board. The third level of performance is what's called a Type C. All gypsum panel manufacturers make these panels, and the point here is to make sure from a design standpoint that you're specifying the right board. From a distribution standpoint, you're shipping the right board, and from a contractor standpoint, you're installing the right board, because if you don't, you run the risk of negating a fire rating. Enough of the gypsum board stuff. 2 hours. Notice we've gone back to an 1 5/8 drywall stud, 18 mil, 24 inches on center, 4 layers of board. We basically doubled the amount of gypsum panel on that wall. 3 hours, still the 1 5/8 25 gauge or 18 mil stud, 24 inches on center, 3 layers of board. And finally 4 hours, 4 layers of board each side, 1 5/8 stud, 18 mil, 125 flange. There are many assemblies that are out there, and I only chose these 4 to give you an essence of what amount of gypsum it takes, and what the steel does in terms of the fire rating. To me, in all the years of testing and designing, the combination of steel for its elasticity and resilience to gypsum panels for either its fire resistance or mass, as we'll soon learn in fire sound, it's a marriage made in heaven, if you will. They work so well together. Think of that. You get 4 hours of separation, and that's after being hit with water for 5 minutes at 45 psi. That stud is still in place, and it's a 25 or 18 mil stud. At that point, all the exposed board is gone. The fire has pretty much consumed it. It's calcined, or it's disappeared. But the stud has stayed in place. The stud has kept its ability to hold screws and therefore gypsum panels on the opposite side. And I can't underscore that enough. That is critical, because if you lose your holding power of being able to hold the fastener and keep that panel in place and in plane, you lose your fire test. Steel plays a key role in fire resistance. Shifting gears, I'm now going to talk about acoustics. We're going to talk about a little of the science of acoustics, and then we're going to talk about the 5 factors that influence sound performance, and finally look at some, I'm going to call them high-end or high STC cold form steel assemblies. You can get some really good sound performing walls that are highly economical using metal studs along with cold form steel. And when we're done, you'll have a better understanding of why that's possible. Briefly, acoustics. I'm going to give you what could be a 4-year curriculum in college down to 30 seconds. Acoustics is the science of sound. The basic definitions of what's up there is sound is defined as a vibration in an elastic medium. Air is a very good medium for transmitting sounds, as well as water. Sound travels similar to waves of water and radiating outward in pressure waves. Most of us, well, I say most of us, I assume most of us have experienced standing in front of a large speaker at a rock concert and actually felt the sound waves. Especially noticeable are the lower bass sounds, and this is understandable when you realize that the wavelengths of those lower sound waves are as much as 57 feet in length. A cycle is one complete sound wave, and you kind of can think of it this way. You have an air molecule. It's excited by sound energy, so it gets a positive charge. So it's going up in the positive range. It loses the positive side. It goes to a negative side, goes back through its set position, and then eventually comes back to rest at that zero plane. So you have a positive and a negative. And if you remember your mathematics, it's like a sine wave, S-I-N-E, sine wave that it produces. And that is what one wave is. And when you look at it in terms of number of cycles, that's called frequency. And so frequency is the number of cycles per second. And in the sound world, it's called hertz. The range of frequency that the normal ear, the range of frequency that the normal human ear can perceive is approximately 20 cycles per second, which is extremely low, to 20,000 cycles or hertz at the high end. That's significant when we start talking about STC because sound transmission classification tests only look at what might be considered the speech range, and we'll get more into that in a second. Amplitude is just the same as volume. It's that volume control on your TV set or your remote, or you still have an old-fashioned stereo like I do. It's the control knob that varies the loudness. A normal office environment is considered to be in the range of 40 to 60 decibels. Decibels, one of the neat things about acoustics is the range of values are extremely huge, and to work with it, acousticians have gone to logarithms, base 10 logarithms, to help handle and make it more linear in being able to determine sound transmission classification and other items. And you're probably wondering why I've got pictures of steel framing alongside this basics of sound, because the last bullet we're going to talk about is sound transmission classification, and that is a single number ratings system that gives us an idea, a comparative way of evaluating different assemblies for impeding the flow of sound through it. So again, we take a look at a total system. We're going to measure it in terms of sound transmission through that total system, and one of the key elements in that system is a cold form steel stud. It has some really good properties for controlling sound in a partition, in floor sitting assembly, and anything. 5 factors that influence acoustical performance. The first one is mass. You need mass. Mass is probably the single biggest inhibitor for sound transmission for that 57-foot wave. You need it for low frequency sounds. And if I take that mass and if I divide it in 2 and move it apart a little bit so they're apart from each other, I can increase the impedance or the resistance of sound to go through those 2 masses. If I double the single mass, I can pick up maybe 5 points of STC. If I double the distance between 2 masses that I've put up, double the distance between the 2 masses that I put up, I pick up maybe another 5 points in an STC rating. My point there is mass alone, isolation alone, is not enough to give us a full highly performing partition. Decoupling, what does that mean? Do you remember when you were a kid and you had a friend and you had tin cans, 2 tin cans, you tied a string between them, you pulled the string taut, and the one kid would talk into one tin can while the other kid at the other tin can could listen to every word he said? Well, that phenomenon occurs in partitions, and that's what really hurts sound performance. So we need to decouple by design, decouple or cut the string to make sure that those 2 masses, or what will eventually be layers of drywall, are isolated from each other and decoupled from each other. The last positive side of influences on acoustical performance is absorption. As sound waves or sound energy goes through a blanket, a sound blanket, glass, mineral fiber, what it does is it starts the individual fibers of that insulation to start moving, and it effectively transfers sound energy into heat energy, thus reducing the sound energy. So we get another net loss in sound transfer through an assembly if we add absorption. So we have 4 positives now, 1 negative. The negative is flanking. And it's a surefire way of killing what could be an otherwise good sound performing wall or floor ceiling assembly. I'll take a moment here in this next slide, give you an idea of how we run a sound test. Basically, we have 2 rooms. This one is called the source room. We've got a loudspeaker here, and we have a receiving microphone on this room, and the only thing that isolates these 2 rooms is this wall here. No sound is able to go this way. No sound is able to go underneath. The only way it can get to that microphone is to go through the wall that I want tested. So I generate sound in this side. I'm going to start, if you look at this graph here, at 125 cycles per second. That's extremely low. And I'm going to run it through 16 different frequencies up to a maximum of 4,000 cycles per second. But at each frequency, I'm going to measure, I know the sound level here, I'm going to measure the sound level in this room, the difference being the transmission loss, or TL, and it's affected by this wall. So that becomes a plot on this graph, and that's what you see here. The black line is the plot of TL, or the TL curve, as we go through the different frequencies. To get our STC value, we overlay that with an ASTM mandated STC contour curve. That's the red line. And that red line, I graphically move up or down until I have a specific amount of points below that red line. Once I've established a location for the red line, I simply look at 500 cycles per second, draw a line up, and where that line hits the red line, so I'm looking at the purple line where it hits the red line, that is my STC, which in this case is a 39. One of the things I want you to be aware of is if you look at that black line again, that is the response of that particular wall at those 16 frequencies. If I build another wall and have different components and I get the same 39 STC, it does not mean that wall will perform the same at each one of those 16 frequencies. I could have a wall that's very good from a sound transmission standpoint at a specific frequency, but lousy at another. So when I compare the two walls, the one wall may not be appropriate for the application I have in mind. And that's why we hire acoustical engineers. They evaluate and they love that stuff, and they make sure you've got the right wall in the right place for the right application. Now we're going to start building walls just like we did in fire. We're now going to do it for sound. The base wall is a 3 5/8 inch, 18 mil stud, 24 inches on center. I've got a layer of wallboard on each side. I'm hit with a net, or my net is a 43 STC when I run it through the test chamber. 43 STC is not bad. 50 is considered a benchmark of quality wall. Some codes now dictate a 55, some a 45, but a 43 is not necessarily bad. But look what happens when I make that stud stiffer. If I put in a wood stud, it drops down to 37. I've lost 6 points. And if I look over here, my mass is the same. The isolation is the same, the distance between the two mass, but the decoupling is different. That 18 mil stud is a pretty good decoupler of those two separated masses. The wood stud, because of its stiffness, is not, and the net result is a 6-point drop. Will I hear 6 points? Absolutely. Absolutely, you will hear that difference. 1 or 2 points on an STC, no, you won't hear it, but 6 you will. If I take that same 3 5/8 inch stud, same mass, the same layers of board, so I've got the mass the same, the isolation is the same, the decoupling the same because I'm using the same stud, and I add insulation to the stud cavity, I've popped up to a 48. So that's a 5-point gain in STC. That's significant. Single layer board, each side, 18 mil stud, 48 STC, that's a good wall. But look what happens when I cut the string even more. If I put a resilient channel in there, I pop that one up from a 48 to a 54. So I have the mass, same. Absorption is same. Isolation the same, well, a little bit more because it's a 1/2 inch more away. But I've decoupled, I've gained 6 points. Interesting thing here, when resilient channels first came out, they were designed for wood frame construction. And I had the blessing to know the guy that developed the RC1 channel, and a great guy. But anyway, we never wanted them used with steel studs, and we were adamant about it. You cannot use resilient channels on steel studs. And it was our contractor partners that proved us wrong. They kept saying, yeah, you can do it, yeah, you can do it. Our concern was rattling. We thought steel-to-steel contact would not be good. We were proved wrong, which really points to the partnership that we have with everybody in the construction industry. But here we have a 54 STC, single air board each side. You'll be hard-pressed to get a better system with that amount of wallboard. 61 STC, we're adding mass. We doubled the mass, decoupled absorption, and the isolation being the same, but we've gone up to a 61. That is high-end STC values. High performance assemblies. This is what you're going to find when you look at, let's say, theater wall construction, where you really need to get high-end and you really need to control low frequencies. But we totally decoupled. We have 2 rows of studs. We double the amount of absorption. We have 2 rows of insulation. Actually, surprisingly enough, you haven't added that much mass. You're still 3 layers of board, but you're a 64 STC. That's huge. 66 if I put double layer each side. Those are phenomenal walls. If you want to use a single row of studs, you don't want to go to a double roll, here you go. You get a 61 STC with a resilient channel, 4 layers of board. A 64 STC with 4 layers of board each side. Point being, you get tremendous STCs with cold form steel framed assemblies. Again, it's the marriage of those 2 materials. The steel stud gives you the resiliency, the elasticity to decouple the wall. The gypsum board gives you the mass. Again, a marriage made in heaven. I was taught early on, Mies van der Rohe said, God is in the details, and that is so true in acoustics. You could look at it as a corollary to that, which is the devil is in the details. If you look at this partition here, it's a section, there's your head and there's your base. If I take that partition and say it's a 50 STC partition and I punch a 1 square inch hole that goes all the way through, in other words, through the one board and through the other, that 50 STC wall will drop by 10 points. That is a huge difference. That is the difference between a satisfied client and a lawsuit. And you're thinking to yourself, well, I'll see a 1 square inch hole. But 1 square inch is 1 square inch. It can come at you if it's a 1/16 of an inch wide, 16 inches long. Will you see that one? Maybe not. I've done a lot of forensic work on acoustical assemblies, hotels, and so on and so forth, condos where they didn't get the sound ratings that they wanted, and it was usually the result of poor planning or installation regarding flanking, and that's what these details are covering. The red dots, acoustical sealant, that's the appropriate application or location for acoustical sealant. I don't need it underneath the runner track. I just want a dollop of acoustical caulk that is in intimate contact with the bottom of the board or top of the board, the structure itself, and the leg of the track. Coming over here, we have electrical boxes. The minute you put an electrical box in a sound rated partition, you impact the sound performance. And you would never want to put outlet boxes back to back, nor would you want to put outlet boxes in the same stud cavity. So what you're looking at in this detail is there's a box here, here's a box 1 stud cavity over. What I'm not showing in this detail is you should put what's called an acoustical pad that totally encapsulates that outlet box. So you're totally trying to seal that box from any sound coming through. Down here, you're seeing a sound rated wall hitting a gypsum ceiling, and it's important that we break that ceiling. Otherwise, that ceiling will act as the string between two tin cans and conduct sound over the top of the wall like that wall was not even there. Moisture migration, moving into the next building science. One of the men I met as an early engineer was an engineer, and I would drive him home from work at times. And one time we were driving home, and he was kind of staring out the window, and all of a sudden he said, you know, the biggest problem in building design is water. Either getting it into the building or keeping it out. And it's such a simple statement, but how powerful. Anybody that owns a home knows the problem with water, keeping it out or getting it in, wells going dry or just window leakage. And water is a unique demon. It comes at us in three phases: solid, liquid, gas. And each one of those phases is a problem for us, or a problem for building components. Ice, spalling a concrete, or ponding and tearing apart building materials through that freeze-thaw cycle, or just heaving the soils around a structure can destroy the structure. Water in its liquid state, yeah, you can imagine that. Wind-driven rain being driven through the wall. Water in its gaseous state, vapor state, puts us into following the ideal gas laws, where we have, as you can see, a wet environment and a dry environment. And what the ideal gas laws tell us is it's going to set up a moisture drive that's going to drive water in its vapor state through that wall, because that wet is going to try to get to dry, and it's going to blow through anything that it can that's water permeable. The bottom line in all framed assemblies, or actually any assembly, is to keep water out of. Keep water out of the stud cavity. I don't care if it's a wood stud, steel stud, I don't even care if it's a CMU wall. You've got to keep water out of that cavity or you're going to have problems. What we're showing here is a water barrier. So assuming this is a wet environment, water in its liquid state is going to stop here. It's not going to get into the stud cavity. So this is the principle that you got to keep in mind. We've got to keep water out of the stud cavity. We have to provide a water barrier to keep water away, and we have to protect any water-sensitive materials. Bottom line is protect that stud cavity at all costs. From a vapor state, this one gets a little bit more tricky because water as a vapor can get through and get back up in here, and if the temperature is such, you can get a drainage plane. Typically it's on the inside face of the gypsum sheathing or sheathing, whatever it is, and it'll condense there, and now you got water in a liquid state. So you've got to be very careful on the exterior walls for vapor drives that could condense because you have a temperature differential from one side of the wall to the other. Acknowledging that a water barrier is not enough. When you have water that's getting back to that water barrier, you got to get it out. And that's done through flashing and through weeps. Simple details. Here's a 3-stud corner. Here's a 2-stud corner. These are defined by ASTM C754. From my standpoint, I don't particularly care which one you use. I think both of them are effective, but the one thing I will caution you with is certain municipalities in, let's say, healthcare facilities require that you go to the 2-stud corner because they want to see that wall board continuous all the way through. When I used to work with architects on designing corners, what I would do, going back to the days of triangles and squares and parallels, is put a triangle right in that location and then rotate it 360 degrees. And as I rotated through that 360 degrees, if I came across somewhere on that triangle a line where there was no gypsum board, I had a problem, so I had to fix it. Very simple, pragmatic way of doing it. But the point is, from a detail standpoint, the 3-stud or the 2-stud, either one works. The abutting for a non-load bearing application is, notice how this stud here is not slammed tight up against this wall. It's backed away. 2.5 inches. And the reason for that is to allow a mechanic to get a drywall screw in here and get it perpendicular or normal to the plane of the gypsum panel so it seats properly. I see a lot of architectural details both in the corner and in this abutting where they take the studs and jam them together as close as they can. It doesn't work from a contractor standpoint. You got to separate them. Typical door frame detail, I'm showing a double stud in a box configuration. You can nest the studs, which means they overlap each other, so it's basically the width of one stud, or you can do them back to back. I prefer the box. I think it's the best way to install it. The nesting, I was working on a project overseas recently, and they demanded the nested stud, and it just became a problem all the way throughout the project, from the frames not fitting to the board splaying out, just a nightmare. Sizing these jam studs, I refer you to go to the Gypsum Construction Handbook for non-load-bearing applications. They have some guidelines based on the size of the opening and the weight of the door.
Now we will do a simple design exercise that will illustrate what we have learned today. The basis of design for this exercise is to design a partition to meet the following conditions. The wall will be an interior non-structural wall that will require a paint finish. The local code requires that a wall shall have a fire resistance rating of 2 hours. The required wall height for this application is 11 feet. And since it is an interior partition, it must have the capacity to resist a 5 psf lateral load. The last of these 4 requirements is that the wall itself must achieve a 52 STC rating. Starting with fire resistance and reviewing the Steel Framing Alliance, a guide to fire and acoustical data for steel floor, wall and roof assemblies, it is determined that the best solution is to follow UL Design U411. This system is comprised of 2 layers of Type X gypsum panels installed on both sides of a 2.5 inch 18 mil stud that is spaced at 24 inches on center. Joint finishing for this particular design, that is the joints between the gypsum panels themselves, may or may not be required. This is a very unique situation for fire resistance testing, but in this case, because it also has to have an acoustical rating, the joints must be finished. Also, for fire resistance in this particular assembly, insulation in the stud cavity is not required. With these materials and in this installation, we have now met the requirements for fire resistance. The heights that a cold-formed steel-framed wall can span is based on an analysis that looks at the deflection of the wall, the interaction capacity of the framing members, and the bending stress of the steel stud as well. Heights are calculated based on these 3 considerations, and the lowest height attainable is then used for design of the wall. The deflection limit is based on the finished material. The equation is based on limiting the span by a ratio that takes the flexibility of the finished materials into consideration. For example, a gypsum panel with a paint finish is more elastic than a finish of gypsum plaster in paint. The gypsum panel is then limited to a deflection at a ratio of L/240, where L equals the span in inches. Plaster, being more brittle, is therefore limited to L/360. An example of this would be a 10-foot wall is 120 inches, and at L/240 the deflection is limited to 120/240, or 1/2 an inch. The plaster assembly is limited to 120 over 360 or 1/3 of an inch. End reaction shear is a function of the steel thickness of the stud and the stud's depth. As the wall gets higher, the end reaction of the head and base of the wall reaches a point where the web at these locations will buckle. Bending stress is a function of the yield strength of the steel and the geometric properties of the stud. The height of the wall is limited below the maximum allowable bending stress of the stud itself. So for our design example, we have the givens. The wall has a height of 11 feet. It is an interior wall and therefore subject only to a 5 psf lateral load. And since it is drywall with a paint finish, we will limit deflection to L over 240. To find the depth, thickness, and spacing of the stud, we turn to the Technical Guide for Cold Form Steel Framing Products, published by the Steel Framing Industry Association. This guide is available online at www.steelframingassociation.org. The data in this guide is based upon the 2016 American Iron and Steel Institute's S100-16 North American specification for the design of cold-formed steel structural members. It is also based on the 2015 AISI S240-15, which is the North American specification for cold-formed steel structural framing, and meets the requirements of the IBC 2018 Building Code, as well as the 2016 California Building Code and 2017 Florida Building Code. This pamphlet is full of tables that covers many applications, including floor framing systems, single and multiple span. It covers interior structural loads or load-bearing walls. It covers exterior walls that are non-structural but carry wind loads, curtain wall applications, and as well as exterior loads that take both wind load and structural based loading requirements. The limiting heights that we will choose comes from the table shown here. It is the interior non-structural composite. In the interior non-structural category of limiting height tables, there are two separate sectors. One is based on the composite action of the gypsum board and the steel framing. The other one is based on steel properties alone. For this exercise, we have chosen to use the composite table. This offers the designer significantly greater heights than if the stud properties alone table is used. However, there are some special considerations that have to take place before this table can be used. One of which is that the gypsum board on both sides of the stud must go for the full height of the wall itself. Looking closer at this table, we will look at 5 psf, and we've limited deflection to L over 240. Therefore, we will focus on the column bordered in red. From a design standpoint, specifically acoustic, we really want to keep the stud spacing as much as possible to 24 inches on center. We also want to go, for economy reasons, to the thinnest steel stud possible. And so based on those two considerations in the wall and deflection, the appropriate stud to use in this application is a 250 S125 18 mil stud that is based 24 inches on center. That's a 2.5 inch deep 18 mil stud with an 1.25 inch flange. Well, we have the fire rating, meaning the layers of gypsum board that's required. The steel stud, which is 2.5, thickness of 18 mil. Now it's time to look at acoustics. Looking at the SFA document, we find that a 2.5 inch 18 mil stud with a total of 4 layers of Type X gypsum wallboard with 2.5 inches of insulation in the cavity yields a 55 STC. Now this exceeds our requirement, so essentially we have covered the design analysis and now have a complete package that looks at fire, sound, and structural performance requirements of this particular consideration. So for this design, we are looking at a system solution that utilizes a 2.5 inch deep, 1.25 inch stud that is 18 mils thick, spaced 24 inches on center. The gypsum wallboard is a double layer on each side of 5/8 inch Type X board. The insulation is 2.5 inch glass fiber insulation in the stud cavity. Now, since there is no water pressure driving moisture through that wall, this is an interior application. There is no requirement for a water barrier.
This completes the formal part, and in summer we gave a background in cold form steel framing. We did some building science and fire resistance. We looked at acoustics. We looked at the marriage of how steel framing and gypsum board works extremely well in both cases. We looked at moisture migration, and finally details, and came up with a design.